without further ado, hey Bruce, how you doing?
I'm doing great, Chris. Good to see you.
Yeah, good to see you too, man. Thanks for coming in. This is going to be fun. Just to sort of get the ball rolling, I know there's going to be so much value in the stuff for anybody that's interested in recording music, audio, things in the studio, things about musical instruments, all the gear involved. It's just for anybody that's into it, they're really into it. So I think that we're all in for a treat. Let's get going. I'm a believer in fundamentals. So let's start with what's Ohm's law and what's it all about concerning audio recording and music recording?
Well, Ohm's law is the key to understanding electronics. And of course, electronics is in our lives everywhere, not just in music. But in the past many decades, it's kind of become more and more important in the world of music. I got into electronics basically when I was a kid. I was one of those people that used to take things apart to see how they work. It gave me kind of a background in mechanical things, and then I started branching out a little bit into understanding electrical things. When I was in high school, I had a couple of years of electronics courses in high school. I was fortunate they offered it as an elective when I was going. And I was also fortunate they were teaching tube circuitry back then.
Oh, we're going to get to
This was in the 60s.
Yeah.
So I had that foundation. And in all the years I played in bands, I was always the guy that would fix the PA when it went on the fritz or fix the guitar amp. And being the keyboard player, I was always having to work on my own equipment. If it was electronic, of course. That kind of got me into a balance of music and
technology and electronics.
That's right.
Yeah, well, when I bring up Ohm's law, obviously for those who know, it's V equals IR, which is voltage equals the current times resistance. Now, all this, when we get back to some of the biographical stuff, but I want to pinpoint this because voltage being like potential energy and what's used so often to power things, to change the level on things. And then current is obviously like the water in a river, it's the flow of the electrons, and the resistance is the load and the things that comes together. These things is a fundamental when you come into a studio or anything. Let's talk a little bit about the practical application of the theory and the electronics part of those particular things, with speakers and whatever.
Right. Well, Ohm's law is a way of understanding the relationship between those three things. Voltage is the potential. Voltage would be what you have in a battery. Just sitting there, the battery does nothing, but it contains the potential to do something. So they refer to voltage sometimes as potential. The simplest circuit you could think of maybe would be a flashlight. So you have a battery supplying current through a light bulb to do useful work of lighting the bulb.
So, it's sort of a useful invention.
Yeah. So the voltage supplies the current when you provide a path for that current. If you were to take this battery and just connect a wire from one terminal to the next, you would discharge the battery right away. In doing so, what you would be doing is creating a path for that current. The current would flow pretty heavily because it's just a wire, and the battery would discharge pretty quickly, and then we'd get to a point where it no longer has that potential on it. The battery's discharged. If you, instead of that wire, if we put a light bulb there, the light bulb provides a resistance to that current flow. And
particularly the wire and the filament.
The filament is a very thin wire inside the light bulb. You're just passing so much current through it that it starts glowing. It's in a vacuum so that it doesn't vaporize and burn up. Basically, the current passing through the light bulb is doing the work of lighting the filament, of making the filament.
The transfer of energy.
Yeah. The light bulb has a specific resistance. The Ohm's law states that current equals voltage divided by resistance. You would have a specific amount of current flowing through that light bulb. If you connected a second light bulb to the same circuit, you would have a second path for that current, and twice the current would flow, and you would discharge that battery twice as quickly.
I get it. So in applications for audio, we have things like speakers and microphones, which are transducers. It's a similar transfer of energy to create a desired result. So when you talk about, for instance, let's start with a microphone and the energy that comes from the sound pushing the air, and then that obviously hits a diaphragm and a magnet. And how does that follow the signal path?
A microphone, basically, especially this one, this is a dynamic mic, and a dynamic mic has a moving coil. It's actually very much like a speaker.
Reverse, kind of, right?
In reverse, that's right. In fact, they used to call speakers dynamic speakers because they could be used as a microphone also. So in a case of a speaker is maybe easier to understand. You have a cone, and there's a coil of wire attached to the back of the cone. That coil of wire rides in a magnetic gap. And when you pass current through that, again, when I refer to current, I'm talking about in that the case of the light bulb, the current passing through the filament is what does the job for us, creates useful work. In the case of a speaker, it's the current passing through that coil. When you pass current through a coil, it generates a magnetic field. Now, this coil is generating magnetic field because of the current passing through it. It's sitting in a magnetic gap. Depending on the direction of the current that you pass through that coil, it'll either draw that coil deeper into the magnet or it'll push it out of the magnet.
That's like plus and minus.
Exactly.
Polarity.
It's the polarity, right. And so that's what makes the speaker cone move from a rest position, move forward, and move back. It's one polarity makes it move forward. The other polarity of current makes it move back.
Which is a cycle.
Yeah, one cycle of a signal, of a waveform, if you will. That's a speaker. That's how a speaker works. Now, a microphone, if it works in reverse. If you move, let's go back to our example of a speaker because we're still thinking of it. If you take this cone and you push on it, what you're doing is you're moving a coil of wire through a magnetic gap. When you do that, you generate a voltage. You generate current flowing through that coil.
That's induction, right? Is it inducing a current?
In a sense. So what happens is when you push in on it, you generate a current through the wire that presents itself as voltage at the terminals of the speaker. And then when you pull that cone back out, it generates the opposite voltage. And so audio hitting that would tend to push the cone in and back, depending on the pressure, because audio traveling through the air is a variation in pressure.
And we call that sound.
Yes.
Which would, is a sort of a simple question, but to you, what is sound?
Right. Sound is...
Good question.
It's the transmission of pressure waves through the air. And it is really sound when I suppose you might say it's sound when we hear it, right? It's like
I get the tree in the forest thing.
Otherwise, it's just pressure waves.
Right.
But we're the ones that call it sound because that's how we perceive it.
When we're dealing with a voice or some other source of sound, in electronics, you have a pure sine wave that you're dealing with electricity to some extent, and there's carrier waves and things like that. But with voices, it's a complex waveform. So the reason everybody's voice is different is because you have your sort of fundamental frequency, but then there's modulated, harmonics and things that give it everybody has a different voice.
Right.
And this is what's bringing us into the complexity of music because there's so many different sounds and so many different frequencies involved.
Well, the same is true of instruments. As you point out, it's you could have a violin play A440 and you can have a trumpet play A440. And yet we can tell the difference between them.
Some of us.
Because of the harmonic content. So it consists everything that vibrates. You think of a guitar string vibrating. There's a fundamental frequency that it vibrates at. And if you looked at that under a strobe light, you can actually stop motion it, and you can see that the string is actually bending like this in the middle. It's doing this. And as it vibrates over its entire length, that is the fundamental frequency of that vibrating string. But there's also harmonics. And again, looking at it under a strobe light, you could see that there's a point right in the middle where you actually have another, a shorter wavelength here, half the distance. And from here, you have another one, half the distance to the end. So that's the first harmonic. It's an octave up from the fundamental. And then from there, you add an octave and a half.
And multiples of that.
Exactly. Then another octave, then an octave and a third, and an octave and another octave and a half, and then another octave on top of that. And that's basically, those are all of the, I guess you might say, the string is the easiest one to understand because we can picture these different harmonics as different lengths of the string. So the first harmonic, an octave up, is actually, there's two of those waveforms along the length of the string. It's actually vibrating as the fundamental, but it's also, you've got, it's actually broken up in the middle, and you've got these individual vibrations, an octave up,
Yeah,
going on.
it's interesting
And
to
then-
think of that because, even with like singing, there's harmonies. And it's like a harmony is sort of like a harmonic. You get a third, a fifth, a multiple of the fundamental.
Mhm.
So the musical application in singing and then the electrical application of the timbre, the complex waveform. Complex just means there's more than one waveform going on a carrier wave, which is actually how phones work and all that crazy stuff and radio modulated frequencies. So that's a great building block for what sound is. There's obviously an emotional context to what makes you like something or not like something. Bob Marley used to have a great quote is one thing that's great about music is that when it hits you, you feel no pain. And, there's pleasing sounds and there's displeasing sounds. There's harmony and there's disharmony. So things that are in tune or out of tune. Now, maybe you could talk a little bit about the difference between something that's in harmony and something that's and not in harmony. And this can kind of lead into a conversation we're going to have later about tubes and solid state. But let's talk a little bit about like what makes something sound good.
Well, musically, usually it's when things are close to direct multiples of each other. As we talked about, the harmonic structure of something that vibrates is one thing. Musical scale is a different thing. It's related in the math, but in its application, it's different. In the case of harmonics that we were talking about, the addition or subtraction, or actually the relative levels of the harmonics, actually create the final waveform. And the waveform can be fairly complex because there's a lot of harmonics involved.
And that's what gives everything its unique timbre.
Exactly. Then you can take those things that are generating this entire spectrum of harmonics, and these instruments generate that spectrum of harmonics on each note that they play. So now you can have these instruments playing intervals, different instruments playing different intervals to create this other math that is the musical scale and musical harmonies and things that harmonize well and things that don't harmonize well. Again, things that are direct multiple. A fifth musically is 1.5 times the frequency of the fundamental. So a C, the G, which is the fifth, would be 1.5 times the frequency of the C.
Yeah, I think a lot of people don't, well, unless they're taught this, they don't realize that the degree of science that's actually behind music. And that's the beautiful thing about music is that, you've got the poetic emotional side, but you also have a very scientific, explanation of these things of how they exist in nature. So like when you're trying to tune a guitar, what are you doing? I mean, you obviously, we've picked a root note or a key and you set the first string to a certain pitch, but to get the other strings in tune, what are you actually doing? I mean, you're making them shorter and longer.
You're adjusting the tension of them, so you're affecting the frequency.
And what about, that's the same with the vocal cords then. So your vocal cords, like if you go lower, they're actually getting longer. And if you go higher, they're actually shorter.
Right.
Because the high frequencies are very small. Like a low frequency, like bass note or a 808 in popular music, some people don't realize that like a 60 hertz wave is pretty long. It's like 100 feet or something crazy like that. When you get down there low, it's pretty long.
Okay, a bass guitar, for instance, low E on a bass guitar is 42 hertz. On a Hammond organ, low C is 32. Actually, it's a good thing to remember, 32 hertz on a Hammond. The pipe organs had for their lowest note, had a 32 foot for the lowest C. So the wavelength of that 30 hertz is about 30 feet. Sound travels at 1 foot per millisecond.
Yeah, it's still pretty long.
So 30-foot wavelength for a 30 hertz tone. And then when you go up an octave to 64 hertz, that wavelength is half that. It's or somewhere around 15 feet.
Hey, without getting too deep into musical theory, as you go up the keyboard, things being a half step, a whole step, these are decisions made upon whatever kind of scale that you're, trying to create the style of music or something. But in terms of like a guitar, when you're like back to the tuning, when you have an E string and an A string, each one of those is obviously a different frequency. But then there's a point where when you actually get them in tune, they work together. to create a chord, and then you have another complex result from something a single source.
That's right.
To multiple sources.
Yeah, harmonies will generate other frequencies. There was a composer, Tartini, Italian composer, way back when, and he was writing things for double basses where he would have them play a fifth apart. And what happened was it would actually generate an octave below the lower note that was being played. So what happens is when you combine two frequencies in the air, in space, they will add, when they have a specific relationship of 1 to 1.5. So that's our fifth, our musical fifth that we're talking about. It actually generates a frequency that is 0.5 compared to the one
the
that you started with.
Yeah.
So, and then there were Tibetan monks that were doing the same thing. They could generate lower frequencies than any human voice could do simply by having two guys sing a fifth. And the resultant would be an octave down from the guy who was singing the lower note.
Yeah, it was really cool. I did a record with Mickey Hart from the Grateful Dead with Planet Drum, where he had the monks from Angola doing this chant where they could actually create like multiple tones with their voices, which is not that easy.
They could divide their vocal cords and sing a chord.
It's pretty fascinating. And then I also another great guy who's from Chicago, Howard Levy, who's one of the greatest harmonica players on the planet. One of the few people that can like simultaneously blow out and pull in at the same time to make like a chord on a harmonica, which is like a single note instrument for the most part, although you can do chords or whatever. But talk about, a master of these things to create sounds that are very unique. And, back to the like what's pleasing and unpleasing. I mean, and that's why I was sort of talking about tuning, because, if something's a little out of tune, first of all, you can say it doesn't sound good, but why? Your brain recognizes things, as pleasing when things are sort of in harmony. Well, but when they're not.
When there's that mathematical relationship that we're talking about, then those other harmonics that are generated fit musically with that. And if you have an interval like a half step, then the difference between those is something that doesn't sound good to our ears.
Right. It's displeasing, but I'm just, I'm always been curious with like why that is, it's like what makes that like more pleasing than others. And one, I think part of it is just your brain has its own, cycles and frequencies that it operates on. And there's certain things that it just finds more pleasing than others. It's kind of down to that. And, when we get into talking about tubes and solid state, there's things everybody says, oh, tube sounds so great. Well, solid state can sound good too, but they operate in a sort of a thing where tubes like sort of distort on even harmonics, and solid state like, as more of an odd harmonic thing. And it's like, okay, I guess the brain likes even harmonics more. That's why people like the way tubes sound. So, we'll come back to that. That was really cool. In terms of like the other application of last thing about Ohm's law is like power and power supplies. Everything needs to have power. So like, tube mics need a power supply, console needs a power supply. And here we're dealing with things that are not so small and they can actually become dangerous. I heard something like 1 amp across your heart can kill you. You can have a lot of voltage and get, electrocuted with a lot of voltage, but won't kill you. But if you get an amp.
Yeah, it depends on the frequency too. That was, Tesla was doing that with extremely high voltage, doing these demonstrations. Well, like that guy there with the
man
jumps. Yeah. And he would pull a spark through the air to his finger and through his body. Well, if it's high frequency, what'll happen is it'll travel over the surface of your skin. Low frequencies will travel through the middle of you, and that's what gets through your heart and locks it up.
Have you ever like almost electrocuted yourself?
I've gotten bit a few times. I actually don't try this at home, folks.
Yeah.
This was when I was very young, and I had a fan motor, and I hooked up a wire to it and plugged it into the wall, and it wasn't working. And I wanted to make sure that I was getting power at the motor. So not having a voltmeter to check that with, I figured, well, my fingers, if I just move quickly enough and just brush this thing with my fingers like that, then I'll, if I feel something, I'll know that there's voltage there. Well, the smallest little, instant of passing by, and my whole arm was numb for like hours.
Yeah. I'm glad nothing too serious happened. But
me too.
It brings up an interesting thing. That voltage that was on that plug or whatever it was. The reason that you can get electrocuted because you could become part of the circuit, and that power is looking for a place to go, and it's looking for ground, right? Which is something we're talking about too. When we're talking about grounding in the application of recording and audio and stuff like that in an electrical circuit, talk a little bit about what a ground is and why it's important, and how, like, in that example, you might have been able to do something safer, like insulate yourself with rubber gloves or something.
I should have just got a voltmeter is what I should have done.
Hindsight.
Actually, I kind of knew this, that I wasn't going to kill myself because it wasn't going to pass through my heart. And really the current pretty much went around my fingers, but it was enough to...
But it's looking for ground, right? That's if it's looking for another
No, it was
potential.
looking for a completion of the circuit. See, the thing is with power in the wall, there's two blades, the hot, which is 120 volts, and the neutral, which is 0 volts. Back at your power panel, that neutral is going to be connected to ground, which also your third pin is connected to, and it literally is connected to ground. It will be connected to a cold water pipe or a stake driven into the ground or something. Literally, it is ground potential. So that's where the shock hazard comes in with electricity, is when you complete the circuit to ground through your body by standing, for instance, in water and then touching the hot circuit. That water to the ground, that
becomes the quickest path to ground.
It's looking for the path to ground, like
Right.
you pointed out. In my case, I wasn't giving it a path to ground. I was giving it a path because the hot and neutral were both right there. And so I was giving the hot and neutral. Now, if I was standing in water, I probably would have killed myself doing that. But I wasn't.
And why is
standing
that?
in- Well, because then that would have been the path through the middle of my body.
Right.
And the only path I provided was through my two fingers. And it hurt like hell.
Yeah, I bet it did.
Yeah. So that taught me a very important lesson.
I bet. Yeah. So what about grounding when you talk about two things? One is, power in the wall, having a ground and trying to make all your equipment happy so that it operates how it's designed to operate. And then we got stuff like in a microphone cable, the XLR, and, the three conductors, and how ground comes into play in sort of those scenarios.
Okay, well, in the power scenario, the grounding is really a safety issue. And every piece of equipment, theoretically, you get away with lamps that don't have this, but every serious piece of equipment should have a third pin that is connected to ground, again, literally ground. The idea behind that is that if anything inside the equipment was to fail to the point where, if a component would fail, theoretically, this could happen. I've never seen it happen, but theoretically it could. A component could fail and make the chassis go live with the 120 volts that we're talking about. Now, somebody comes along and picks up this piece of equipment. They're standing on the ground or they're standing in water, which is even better.
And they become
connection
part
to
of the
ground.
circuit.
And they complete that circuit then because the chassis has gone hot. So the idea with the third pin is that third pin on every piece of equipment is connected to the chassis. And so if anything ever goes bad inside the circuitry that is going to want to make that chassis go hot with 120 volts, it'll immediately blow the breaker and shut everything off. And that is because
some people learn that the hard way, probably.
Yeah. So it's simply because that chassis is connected to ground. Now, that ground also is the shielding in terms of the electronic equipment. So over there in your Marshall amp, it has a steel chassis, and all of the circuitry inside that could be susceptible to picking up noise from the outside world is within this shielded enclosure. And that shielded enclosure is connected to the third pin ground. So the idea is that chassis then is always 0 volts. So the noise and crap that's floating around the air around us, anything that is pulling current in this room, the lights, the audio equipment, everything generates a field around us. And that can be picked up by the equipment if we don't shield the equipment against it.
Which in the audio application brings me to one of my favorite questions to drill interns on and graduates from all these recording schools is like the use of balanced and unbalanced cables.
Right.
And what is actually the difference in unbalanced cables. So let's take a minute here and then we'll come back and talk about that.
All right.
All right.
Sounds good.
Great. Let's pick it up where we left off. Anyway, so as I said, I'd like to see, if some of these schools have taught some of the fundamentals. I would say, what's the difference between a balanced and unbalanced cable?
You're asking me?
Yeah.
Okay.
Well, there's no one better to ask.
So balanced audio transmission is something that we get from our phone companies. From way back in the day, they invented this. The idea behind it is if you think about a normal connection like a guitar cable, which is an audio connection from the guitar to the amp, it has a connector on the end that has a tip and a sleeve. So there's two basically paths for the current to follow, and you need two paths. You need a send and return path because the current flows like in a loop. So
And that's unbalanced.
That's unbalanced. And so you have a signal, the signal wire is in the middle of the cable. The cable has a shield around the outside of it that is just a metallic braid that completely encases the signal wire and prevents it from picking up noise from the outside world. It acts as an electrostatic shield because it is connected to ground. So that's basically one way to transmit audio from one place to another. The problem is that no shield is completely perfect. And in some cases, if you have a long distance that you're going with this signal, you're exposing it to more noise and interference from the outside world. And so over the length of this cable, you can pick up enough noise to actually start interfering with the good signal that you're trying to
transmit. And these are things
transmit.
like radio frequency.
Right. Power,
cell phone.
EMF generated by power. Power is all around us. The power connections through the wall travel maybe up over our heads, down below our feet. It's completely encasing us.
So it can get noisy.
Yes. So it generates this massive field of all these different frequencies and noises that our signal can pick up when you have a long cable. So the idea behind balanced audio transmission is that instead of having our path for our current be through a signal wire that's protected, but then returns on a ground that's not protected, the idea is to have the complete path for the audio, send and return loop, on a pair of wires that are twisted around each other, and then that has the protective shield around it. So this requires 3 connections, 2 for the signal and 1 for the shield. What it does is it takes the shield out of the signal path. So any noise that's picked up by the shield is not really part of the signal path. But the real benefit of balanced audio comes in what happens at the receiving end. Basically, the audio that's transmitted on a balanced line, the 2 signal wires, they're basically the same signal, but they're 180 degrees out of phase with each other.
Plus and minus.
Plus and minus. Opposite polarity of each other, if you will. And so what that means is that when one is positive polarity, the other one is negative polarity with the exact same signal. And at the receiving end, the circuitry looks at these 2 signals coming in. Knowing that one is out of phase with the other, it takes that one, inverts the phase of it, and then combines it with the first one, so that you end up with twice the signal at that end. You add those 2 together. But the important thing is that over the length of this transmission wire, any noise that gets through the shield and gets into the signal wires is going to get onto the both signal wires because they're twisted around each other. So no matter which way they're rotated, no matter which way the noise is coming from, it's going to hit both of them equally and get picked up by both of them equally. So what happens is you have the same noise on both polarities of your signal. So when that gets to the receiving end, the circuitry takes the one negative polarity signal, changes it around to positive polarity. It inverts the polarity of it. What happens is it's inverting the polarity of the noise also that got picked up on that line. So when you combine an inverted version of the noise with the non-inverted version of the noise, they cancel each other out.
And which makes it quiet.
And makes it quiet.
And that's done at the connector on the destination point?
Well,
or is it done at the other side of the cable?
Well, you have to have a balanced source that's transmitting a balanced audio. And that can either be created with a transformer, which inherently is very easy to make a balanced circuit using a transformer. Back in the day, that's the only way they did it. Nowadays, you can have electronic devices, electronic circuits that can do the same job of the transformer for about 1/70th of the cost.
Yeah, naturally.
So that's what everyone does nowadays. But transformers still do sound better. They have their own characteristics that make them better to our ears.
Right.
Anyway.
Well, that's rarely the answer I get from recording school graduates, but it's a pretty good one. I don't think anybody knows that that's really designed to help keep it. Well, they might know it keeps it quieter, but not how.
Yeah, and it actually is so effective conceptually that phone transmission never even used a shield. You'd have a 50-pair cable, maybe this big around, that would have 50 conversations going on it. And each one of those is just a simple twisted wire, twisted pair. And these twisted pairs next to each other, they don't crosstalk because they're twisted.
Right.
And they're balanced.
Yeah, it's really pretty cool. The application of the two conductors and the shield XLR, the three conductors, I guess, altogether versus two is usually the description, I guess. Like one's a 2-conductor system and one's a 3-conductor system.
Right.
But why?
Right.
So that's beautiful. And anybody that's done any recording or engineers out there, the bane of our existence is buzzes, hums, and noise. And one of the reasons, besides it being annoying, is that in order to get a wider dynamic range and a more pure signal, you have to minimize your noise floor. And every time you add another source of noise, you're masking your original sound. And it gets, the noise floor goes up and the clarity becomes less clear, and then you got more interaction with the noise frequency. So in a quiet room or a very quiet signal, it sounds better because you're not getting into this. Now, back in the day with analog tape, there would be like hiss noise, and where, some people think, are nostalgic about that's charming. And there might be something to that. There's other reasons why analog is pleasing, but the noise is a funny thing too. I mean, there's definitely ugly noise, and then there's, some noise that's part of an instrument, like on a B3 that rattles and clanks, and, you hear the mechanical stuff. And, when you hear that in a song, that's part of the instrument. So that's
the stuff that we just live with because there's no way around it, basically.
Right, but it's also charming to the extent that tells you that's real.
Yeah, I suppose.
Because most people are like, oh, that's part of the sound. Whereas an engineer, I'm like, oh, can we get rid of that sound? Can we get rid of that thing? And I suppose like everything else, there's a threshold of where it's acceptable, But the whole endless pursuit of like making cables quiet or connections quiet, particularly with guitars. I mean, anybody with a single coil guitar, in the noise that's in the radio frequency range and of the electromagnetism around, if you have a single coil guitar, it really picks up a lot of noise.
Oh yeah. Well, yeah, a Strat, something like that is probably the best way to pick up noise. If you want to pick up noise, that's the best way to do it.
And they have a switch where it's, the other design is a humbucker, which is designed to actually get rid of
speaking of humbucker, that kind of helps clarify a little bit the balanced audio thing. A humbucking pickup, well, single coil pickup is just a coil wrapped around the pole pieces. The pole pieces are underneath each string. When the string vibrates near the pole piece, it generates a current in that coil. The problem is that coil is going to pick up all this noise that we're talking about too, and it certainly does. And as you move the guitar different directions, you're going to find out what directions the noise is coming from, because you'll certainly get it, and then you can cancel it sometimes.
Yeah, it's because of magnetic fields work.
Right. So a humbucking pickup is kind of like our balanced audio. What they do is they put a second coil next to the first one and they wire it out of phase. But it doesn't have the same pole pieces, so it doesn't pick up the strings the same way that the first coil does. So it's there just to pick up the same noise that's being picked up by the first pickup. And because it's wired out of phase, it cancels that out. Now, that's one of the reasons why a Les Paul has less of a top end than a Strat, because a Les Paul with humbuckers, there's a little bit of bleed into that second coil, mainly in the high frequencies. So your high frequencies are going to get canceled out. That's why a humbucker is less high frequencies.
It didn't hurt Zeppelin very much, though.
No, it didn't.
AC/DC.
But it certainly allows you to get a lot more gain without the noise that you can't live with.
Yeah, there's a point where it ruins a sound, but with a single coil, it can get so bad where it's like actually ruining it. And it's definitely something you got to deal with. So obviously there's some solution to that, but half the reasons a lot of times I'll call a tech into the studio will be, hey, there's this ground hum. Where's it coming from? Where's it coming from, Bruce?
A ground loop.
Why is it hum? Because it doesn't know the words.
What you're talking about is a ground loop, and that's something that's pretty common. The classic example of a ground loop is when you have a guitar amp, for instance, out in the studio, and you have it mic'd up, but you also want to take a DI on it. So the guitar player plugs through your DI box that plugs into the amp. Now, the output of the DI box has an XLR cable that plugs into your mic pre or back to your console. Balanced, correct. And that has, on our balanced connection, we have our 2 signal wires, and then we have our ground connection. So there is a ground connection from the chassis of the guitar amp to the console in the control room. Now, at the same time, the guitar amp is plugged into the wall with its 3rd pin ground. Now, that 3rd pin ground is taking the chassis of the amp to the power ground. Now, that's traveling maybe over our heads somewhere else, a different path than the cabling that goes from our DI to the console. So the separation of these 2 paths creates a big loop. You're grounded in 2 places with your amp. You're grounded in the wall and you're grounded to the console. Console is also grounded somewhere to the wall. So that's...
Ideally, it should be on the same ground.
Well, a way to minimize the problems is to have all those grounds from all your outlets go to one point. That's done in a lot of studios to eliminate those ground loop problems. A lot of places, if you didn't do that in advance, then you can run into these problems.
And that's why you need a ground lift.
And that's why DI boxes have a ground lift on them, so that you can do that. The other version, of course, the one that, don't try this at home again, folks, is the 3rd pin lift, which is the little 3-pin to 2-pin adapter. What that does is it disconnects the chassis of the amp from the power ground and allows the amp then to just take its ground from the mic cable that's going up to the console. That's perfectly valid and it's quiet and it works. The problem is if somebody unplugs the DI, then that amp no longer has a ground to its chassis.
And you could get shocked.
You could get shocked. I've seen guitar players get a little buzz from touching their strings and something else.
I've seen guitar players get buzzed too.
Yeah.
In the studio all the time. Well, that's helpful because I think, having that ground loop is another source of noise that can muck up your signal. And it's down there in the more like 60 cycles sort of thing.
Well, it's based on power. What you're picking up with that ground loop, basically the loop itself acts like a big antenna, and then it puts that noise into your ground of your system. And of course, everything is referenced to that ground, and that's why you start to hear it.
But why is it at 60 cycles?
Because that's the noise. The noise that's being generated is based on 60 hertz because it's coming from the power around us.
And the reason that power is at 60 cycles or whatever it's set is alternating current and sort of a Tesla thing, versus DC current.
Right.
Let's
well,
touch on that real quick.
That was Tesla, man, very much ahead of his time. There was a big fight or a big disagreement, you might say, between Tesla and Tom Edison. And they were competing for the contract to light the World's Fair in Chicago, early 1900s, late 1800s, something like that. And Edison had a system that was based on DC, and Tesla had developed a system that was based on AC. He and George Westinghouse developed a system based on AC. Now, the brilliance of AC comes into play when you try and send power over long distances. We touched on Ohm's law a little bit, and Ohm's law states that when you pass current through a resistance, there will be a loss of voltage. There will be a voltage drop through that resistance. So if you're trying to send power from a power generating facility miles away, you're going to need some pretty heavy wire so that you keep the resistance of that wire. The heavier the wire, the lower the resistance. So you want to keep that resistance to a minimum so that you don't lose voltage over those miles that you're trying to send this current. So Tesla's idea was, in using AC, you can convert AC using transformers. You can step up or step down the voltage. When you do that, it follows a very linear relationship. Power, which is what we're dealing with, ultimately all of our calculations kind of come back to power because that's what we are using electricity for. Power to light the lights, power to heat our homes, power to turn up our amp. So anyway, using transformers, you can step up the voltage. If you double the voltage to get the same amount of power down to the receiving end, you need half the current. It's a linear relationship. You quadruple the voltage, you need 1/4 the current to get the same power delivered to that receiving end.
And most regular outlets are designed to be 10 amp or 15 amp and with a certain voltage using AC on the consumer end of, power sources.
Well, we're at 120 in our homes. But
120 what?
120 volts.
Which is also the cycle.
Well, 60 cycles is the frequency, and the voltage is 120 volts. So for when you see power transmission towers, big towers with the lines going from the power generating facility to the city, those things are up at 35,000 volts.
Wow.
So you can imagine that how much higher that is than 120 volts. Well, that's how much less current you need for the same amount of power. So that was Tesla's brilliance, was that by stepping the voltage way up, you can transmit it over thinner wires for longer distances. Then you get to the city, you use a reverse transformer to step it back down. And then when you get to neighborhoods, you've seen on the pole out in back of your house, there's a can like this. Well, that's for you and a couple neighbors. And every few houses, there's another can. Those are transformers that step it back down to the final 120. Actually, it comes into our houses at 240, which is basically two 120s.
But the important takeaway for a studio is to have a common ground and to have a reliable source, the electricity, but that to a degree that's regulated by the power company to an extent. And I think that's part of the advantage of the AC too, right? Is keeping it constant.
Well, that's done to a pretty high standard. Nowadays, they can adjust that pretty closely. So 60 hertz is actually for years was used for clocks.
Which we're going to touch on when we talk about this
about
puppy
the Hammond
here.
organ with a synchronous
The other thing
motor.
we're going to touch on later is the theremin and the way that whole, when you touch it, the current jumps to your fingers and stuff like that.
Yeah.
Tesla had a thing called a Van de Graaff, which was electrostatic. It would jump out.
He was working with real high frequencies, so it was safe to do that. And yes, you could get the voltage up high enough, it'll arc, it'll jump.
Okay, cool. That was a lot of great technical stuff. Let's get into some a little bit more about your story. I mean, what was your childhood like? Was there some influential technical person or a musical talent or somebody in your family that sort of inspired you, or so how did it all begin?
Well, there's two parts to my story. One is music and the other one is electronics. And the music part of it, my parents always had music on at home, show tunes, Oliver, Sound of Music, stuff like that. So I grew up with that.
Fiddler on the Roof.
Yes. So I grew up with that, and they always had music playing. They weren't really musical per se. My dad played harmonica a little bit. He was pretty decent at it. He actually played a chromatic harmonica, which is pretty advanced stuff.
Stevie Wonder does that too.
Yep,
right?
with the button. Yeah. But anyway, so that got me a little bit interested in music. My older brother played in bands. That dragged me a little deeper into music. But then in conjunction with that also, I was a guy that would always take things apart to see how they worked. And eventually got to playing in bands and being the guy who fixed all the stuff that would break in the band.
Cool. What was your first real band?
First real band, because I played in a bunch of garage bands, if you will, or basement bands. But the first real band was a band called the Tobacco Rogues. And I was in the right place at the right time because I played organ. And that was, what was, back then, the songs that I learned for my very first band were 96 Tears by Question Mark and the Mysterians. I could still play it. So I had a Farfisa, which was a little plastic organ made in Italy. And you heard that on a lot of the 60s tunes. This was in the 60s, by the way. So the band that I ended up joining, that was the first serious band, the guitar player had taken a trip to San Francisco to visit his cousin. And when he was out there, this was 67, he saw the Doors live. And he came back and he said, "This is the future of music. We need an organ player in the band." Now, my older brother, was the bass player in that band. So he said, "Well, my younger brother plays organ." So I got the call and I joined that band. That was the first serious band.
And you learned how to play Light My Fire.
And I learned how to play Light My Fire. Exactly.
Yeah. Amongst some other great parts of Ray Manzarek, right?
Yeah.
Or Manzarek. I'm not sure how he likes to have it pronounced. So that's interesting. And then, then you played with a band that had a deal, right? Gambler or something?
Well, yeah. Then all throughout the 70s, that entire decade, I just played in bands, local bar scene. And then in 78, we got signed to EMI and we put out 2 albums. One came out in 79, one came out in 80. And after those 2 albums, we never had the hit single. And so we were dropped. And then I went to DeVry for finish off my electronics degree. I had some training back in high school, a couple of elective courses, but I figured I'd get a serious real job, or what my mom always called a real job.
Yeah,
And
but
so-
before you go too far into that, what was the recording experience like for the deal? You got the 2 records you made. You went in the studio, right?
yeah, well, we did the demos at CRC with Phil Bonanno.
Oh, Phil Bonanno.
Yeah.
He's a legendary engineer. Eye the Tiger.
Yeah, right. And that was rest his soul.
Yeah.
The demos were done at CRC, and then we did the first album with Jeff Glicksman, who produced Kansas, and we did that one down in Atlanta.
Nice lineup there. Yeah.
And then the second one we did with Phil at CRC.
Anything break that you had to fix during those sessions?
Not me. Cleon was on the case then.
Okay. Well, that brings us to another point of the conversation. So anyway, you're in the like 79, 80. That's got to be pretty close because you're going to CRC.
Yeah.
Yeah. Talk about how you made that transition to CRC.
Well, that was kind of a roundabout way, but an interesting little sideline to that was Cleon was the chief tech. And when you say I was the chief, I was only the chief for the last few years.
Cleon Wells.
Cleon was the chief. I was his right-hand man, basically. But when we were doing the second album, I was wandering the halls at CRC one night, and I stumbled on the tech shop. And I'm looking around, and of course, with my background,
There's a funny smell coming from there.
and so I'm seeing all these parts and, raw speakers and like alignment tapes and test gear and stuff. I was like, wow, this is so cool. If I wasn't a musician for a living, this would be a really cool gig to have. So then, yeah. So then after the band got dropped from the label, I went to DeVry to finish off my electronics degree. And at that point, I wasn't even thinking about doing studio tech work. I was just thinking about working for IBM or somebody like that. So before I graduated, I got a call from Phil Bonanno, and he said he was building a studio up in Lake Geneva, and he needed a tech. He knew I was going to DeVry. Would I be interested? So I went up and took a look at the place, and it just hit me like a ton of bricks. This is where I belong.
Was that the beginning of Royal?
That was Royal.
And that's in the old Playboy building.
Right. And that was the what had been the Playboy Resort in Lake Geneva. And he was building that studio to be kind of a resort type facility. That was kind of a thing back in the day.
Oh, yeah.
So I went to work for him and worked up there for a few years. He sold out his ownership and went back to staff at CRC. Then he called me up one day and he said, CRC is looking for a tech to help out in the tech department, to be an assistant to our chief, Cleon. And at that point, the studio up in Lake Geneva was it was under new ownership, and I was a little concerned about the future.
Yeah, there were some dramatic characters that were involved in that whole scene, subject for another day, but
yes,
it's, 80s, a lot of crazy rock and roll stuff there. I mean, it's a perfect place for that too, for, pot for, bad behavior, but also a lot of fun.
Oh, yeah.
Maybe too much fun.
Yes, indeed.
So they get you over to CRC and you meet Cleon, and what was that like?
It was great. Cleon is one of my favorite people I've ever known, and he is just a brilliant guy. He has the gift of being able to just see through the haze and get right to the root of a problem. When something is broken, he'll figure it out right away. Brilliant guy. And every day that I worked with him, I learned something else. I mean, to this day, when I speak to him, I learn something every time. So he's one of those people. And he really helped get my skills up to where they belong, for a place like that.
Very much a specialist sort of thing. I mean, it's one thing to be an electronics engineer, a thing to be a studio tech, I mean, sure, there's a lot of electronics, but there's a lot of other stuff too.
Oh yeah, there was times where we had a plugged up condensate drain, and I'm up on a ladder with the ceiling tiles pulled, and I got my arm over my head, and I'm unscrewing a drain, and water's dripping down my arm. And I said, boy, am I glad I don't do this for a living. Wait a minute, I'm doing this for a living.
So much to learn. It's endless amount of stuff to learn. At that point, it was probably close to the transition of analog into doing some early digital stuff. And, maybe it's pretty close because, when I got started at Warner Brothers in 1985, in my first couple of years, I still cut a lot of tape, but there was digital tape machines coming along down the path. So, analog recording is the foundation of all the early great records everybody ever heard, from not just, tape. I mean, it goes back to the cylinder with Edison and, all that stuff. I mean, stuff that's truly based in the analog world. And then as technology developed, digital audio started to rear its head for, I guess a lot of reasons. I mean, that's just the nature of human beings trying to keep, pushing technology. And there's a lot of, people that build equipment are always trying to find the new greatest thing. But again, going back to the thing about sound, people still to this day, there's a big debate about analog versus digital. And the early appeal with digital was probably the ability to store it and have it be a more exact replica of the original waveforms and not be like, distorted or changed or have any coloration.
Yeah, it was a way to kind of reduce or eliminate, or I should say eliminate or reduce the artifacts and the crap that comes along with these different formats. Tape, of course, signal to noise ratio. Big problem. There's a constant noise floor that just limits your dynamic range.
Wow and flutter.
Wow and flutter is another thing based upon the equipment. The better decks, that's negligible, but still, it's a consideration when you're talking about perfection.
Had you ever opened up a tape machine before you met Cleon or went to CRC? Did you ever have any experience with a tape machine?
Oh yeah, when I was 10 years old, I got my first tape machine, little reel-to-reel, little 5-inch reels, and then I got my first stereo one. I was about 13, and I got a stereo one with detachable speakers. It was pretty cool.
All right. Well, that's a huge discussion that we'll get into at some point about analog versus digital. But going down the timeline still. So you meet Cleon, you start getting, some experience with the recording studio that you're working in at CRC. And that place is unique because it has a couple music rooms and a bunch of post-production rooms. And, in the post-production world, they're trying to move real fast and there's high dollar, clients. And then at night, you got the people that don't care about moving so fast. And because, the big consoles with lots of inputs at that time, they started out, I suppose, in a sort of affordable thing. But when you got up to a 72 input SSL,
you're talking $500,000 to $1 million.
Yeah, it's a big investment.
Yeah.
And for sure, and then you're going to have to charge a lot of money for someone to use it. So when they come in, you can't have it breaking down, so therein lies the role of a studio technician on the spot to keep a session rolling. And, anytime there's a problem, it's I'll call the tech and have the tech come in. And some reason, every time I called you, as soon as you got there, the problem went away. I don't know what that was all about.
That's the tech effect.
Yeah.
Well known.
I swear to God, it was making noise before you got here.
That's right.
But yeah, talk about saving the day, because you could have a room full of musicians all being paid a lot of money, and then the tape machine craps out, and it's they're all sitting there burning money and stuff like that. And you got the producers looking at you, staring at the studio owner, going, "Hey, man." Who's going to pay for this? So you're really under the gun to be able to fix that stuff quick. So, real quick, sort of that had been kind of exciting too, but also kind of nerve-wracking.
Well, yeah, it was. Every session was different, and there was different challenges. It wasn't always stuff breaking. Usually the equipment didn't break as much as...
Well, if you're doing your job again, yeah.
What was that?
If you're doing your job maintaining it well, I suppose, but shit happens.
Well, and equipment at that level, when you pay $500,000 for a console, it's designed to never break down. Those consoles were used in broadcasts too, where there's no excuses. There's no second take.
Yeah,
you can't tell everybody to just take 5 while you fix this. It just can't go down. So equipment at that level is really designed to run pretty much uninterrupted 24/7. It was more individual needs. How do we do this? We want to try and do this. How can we pull this off?
Yeah, sometimes you don't have somebody how to use the new technology.
Sometimes sometimes solving problems that were created elsewhere. We had a tape once that came in from another studio, which I won't name. It was for a big name client who I will not name either, but they had done some transfers that were not syncing up, and we had to invent a way to get the slave reel. Now, this is back in the day when we would link to digital machines,
right,
to Mitsubishi X850s.
Yeah, I got some stories to share about that, but go on.
Which would give you 64 channels to record on. And they had done all their background vocals on the slave reel. So all of a sudden, we're trying to mix this thing, and the background vocals are drifting against the music track. So we realized that they had screwed up when they did the transfer, and they didn't transfer the time code properly.
Well, here's where I have kind of a loaded question that's pertinent. What do you think's the most common problem in the studio? Think about what you just said, operator error. I mean, and that's understandable because you're dealing with a lot of new technology and crazy stuff. But a lot of times, you're right, the equipment's not breaking. Someone just did something wrong and needs help figuring out how to do it right.
Yeah.
Your example is a perfect example of that. I mean, and again, that's some high pressure stuff because if that doesn't sync up, like everything you just did doesn't work together anymore. So, like a lot of the cool techniques in recording were invented, like they say, necessity is the mother of invention, like creating tape echoes and all that stuff that they we didn't have, even people before me, they didn't have plugins and stuff like that. They wanted a delay. They had to think of a way to delay the signal.
Yeah.
And that's probably some of the most fascinating stuff to people who grow up now who never will experience that sort of
things like live chambers, real live chamber. Right now you have it in a box. It's all digital.
Right.
Back in the day, it was a room with a speaker and a couple of microphones.
Yeah, like the Capitol chambers are famous for like that Sinatra sound or the Beatles sound. You can actually, through ISDN digital phone lines, probably even some newer now, tap in and rent those chambers. They're underneath the parking lot. Yeah. They preserved them, which is awesome. Yep. But you can also buy the UAD plug-in and simulate the Capitol chambers for $100. So yeah, it's a different feeling for sure. And when I say the operator error thing, that comes from having made a ton of mistakes myself and needing someone that has a higher level of knowledge. But right off the bat, whatever new equipment came in, you had to know it inside out, or at least a lot of it. So that probably that probably had pros and cons. And it was great to play with all the new equipment, but to the extent that someone else is using it, you get to get the satisfaction from seeing it work and yield the cool results. And that's heroic, because if you get the session off the ground and then a hit song comes together, it's like then you really see the team being able to celebrate. The opposite of that is something that breaks and can't be fixed like immediately, and session's over. We got to order a part. That stuff happened too, right? Some have to cancel something, or rarely, but
it was rare.
It's because you had to get a part or something. Well, okay, this might be a good time for another quick break. I think that much stuff in that range of studio equipment, but I really like the fact that we talked about the fundamentals, because to help offer value to people that will see this or watch this and learn stuff, it really, really is important to know like some of the basic stuff. I mean, it's also important just to know what to use. Like one of the first things I remember is like when I saw a big console, I was like, man, what do all those buttons do? I'll never figure this out. Well, it became clear to me, I just need to figure out how to get a microphone up and get it to the tape machine, and I'll worry about the rest of the buttons later. Just one thing at a time. But yeah, the fundamental stuff, I can't stress that enough. And we're going to touch a little bit more on that when we come back.